Hello everyone and welcome to another problem solving session on Special Maths Academy. And today's video we are going to come with the 24th problem from the Senior First Round Maths Olympiad, and it goes like this. In R3, that is the three-dimensional space, lattice points are points with integer coordinates. It is known that in any set of k lattice points, there exist two distinct elements whose midpoint is also a lattice point, not necessarily in the set, that's of the set of the k lattice points we have. So what is the maximum possible value of k? So this is how the question goes exactly. But I think there's a problem in the question. I think this maximum is meant to be replaced with minimum, because that is the only extremum that makes sense. For example, now if we have like 1,000, for example, now if given any set of 8 lattice points, or let's say let's say in a set of 100 lattice points, like 100 lattice points satisfies it, then any number of lattice points bigger than something that satisfies it is also going to work. So the only extremum that will be reasonable here to find is the minimum, not the maximum. So the question is meant to be what is the minimum possible value of k? So that's what we are going to solve. I don't know, maybe it's a typographical error, yeah, but this is what we're going to solve. Because the maximum, it has no maximum. It doesn't have an upper bound, but it has a lower bound. Okay. So now R3, okay, R3, the set in the three-dimensional space can be represented as three numbers, maybe x, y, z. Just like for R2, that's coordinate geometry, has two terms, like two numbers in the brackets, a tuple. Oh, yeah. So, but this one is a treble. Yeah. So this one, then lattice points here means that these three numbers, they are all integers. So I could have just written all of them together as integers, but so let's write it this way. And also in minimum, midpoint is between 2 points, let's say A, B, and C, and D, E, and F. The midpoint of these 2 points is going to be, as we may have expected, a lot of properties of two-dimensional coordinates transfers to three-dimensional ball. So this is the midpoint of these 2 points, A, B, C, and D, E, F. This is the midpoint. Just take the average of each of the corresponding corresponding quantities, like in each component, the X component, Y component, and Z component. So with all this now, we have defined everything in the question. So it says, what is the minimum possible value of k? So like, what is the smallest possible value of numbers we can have, such that among those numbers, among those lattice points we have, that there will be two we can add up that will give us integer, that will give us also lattice point, that the midpoint of those two we consider the lattice points. So remember, for the midpoints to be lattice points, each of these terms have to be integers, remember. So what does that mean? It means that A plus D should be a multiple of 2, B plus E should also be a multiple of 2, and C plus F should also be a multiple of 2. So that can translate to A and D have the same parity. Like, parity just means even or odd. Like A and B are both even, or A and B are both odd. That's what A and B has the same parity mean. D and E also have the same parity, and C and F also have the same parity. So this question is really pointing down to pigeonhole principle, and from these observations, we will now be able to deduce what exactly we have to do. So now let's say we have k lattice points. Let's call it x1, okay, x1, y1, z1. You know, this comma looks like 1. Okay, I'll call it x1. Okay, I'll put this now to differentiate it. Like this still, let's say we have k of them, and k is the minimum, So remember, for 2 points to have the same, for the midpoint of 2 points to be lattice points, it means that the corresponding components should both have the same parity. For example, now let's say these 2 points, the midpoint is a lattice point. So it means that x1 and xk should have the same parity. Y1 and yk should also have the same parity, and z1 and zk should also have the same parity. So first of all, we have to count the possible number of different parities each component can take. So remember, there are only two possible parities, and two parities are even and odd. So it can either be the first is odd, odd, odd. O stands for odd, E stands for even. This is not really zero, it's just O. Odd, even, odd. Odd, odd, even. There's actually no point of writing all these things down, but by simple counting, it's just easy to notice that for each of these components, it can either be odd or even. So each of them takes two possible cases. And because they are all independent, we can multiply them together, and we don't really subtract any intersection. So what does this mean? It means that there are 8 possible configurations. Like if we just take mode 2 of each of the components. So there are 8 possible configurations among these odd, 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 even, odd. Let me just write all the 8 possible ones. Odd, even, even, odd, odd. Okay, I've written all the ones that start with odd. Even, odd, odd, even, odd, even, 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 odd, and what? I'm right, the last one. Even, even, even. Even, even, even. So these are the 8 possible configurations if you take mode 2 of each of the components. So now, if we have at least 9, if we have 8, so it means that, for example, now, if we have a number like a vertex that is like a member of each of these individual ones, like there is no one that has at least 2 points in each of the sets. For example, now let me just give a concrete example. For example, now 5, 1, 2. What is the 5 is odd, 1 is even, 1 is odd also, and 2 is even. So this 5, 1, 2 will be a member of this one. Will be a member of this one here. So that's what I mean. So what I'm saying now is that if we have if we don't have up to 9 terms, like 9 points, we can like make a very weird way, just that it has a very low probability, but we can like choose one vertex lattice point from this, one 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 from this, and one from this. So that would be 8. And notice, like for the midpoint of 2, for the midpoint of 2, for the midpoint of 2 points to also be a lattice point, those 2 points have to be a member of one exact of this 8 group. It has to be like a member of one of this group. Those 2 points have to be inside this group, inside one of this group. You can, it's not so difficult to see why. You can just try and check it out on your own. But both of them have to be a member of one particular group for their midpoint to be a lattice point. So if we don't have up to 9 terms, like they can, it means that they can be a way we can just choose at most one in each group, and in that particular configuration, we'll not be able to like get 2 points at their midpoint to be a lattice point. Because for example, now if you had an odd to this, okay, odd plus odd is even. So if you divide by 2 is a whole number, that's cool. Odd plus even, that's where we'll have problems. So it won't be a whole number. So when one of the terms here is not a whole number, it's already breaks the definition of a lattice point. So that's why I say like for 2 points to have a lattice midpoint, then both of those points should be a member of either of these 8 groups. Like both of them should be inside one of these 8 groups. So if we have 8 points or less, we can choose some numbers that, like, we can make sure that no number will be no lattice points will occur. No 2 lattice points will occur in one of these 8 groups. So it means that the answer should be at least 8. Should be greater than 8. So when we have 9 and above numbers now, you know that when we have 9 numbers or greater than or equals to 9 numbers, then by pigeonhole principle, since there are 8 pigeonholes, that's like this odd, odd, even, odd stuff. Since there are 8 of them, there will be a group that has at least 2 numbers in it by pigeonhole principle. So when we choose those two numbers will have a lattice point based on what I explained earlier on. So that's how to do this question. It's just pigeonhole principle. That was like the major idea. And to be able to like find out how many, like how we could interpret this question from midpoint, from lattice point, midpoint, we translated to odd, odd, and parity stuff. So that was just like the main idea in this question. So the answer to this question is 9, because if we have at least 9 points, then by pigeonhole principle, at least 2 of those points will be inside one of these groups. And those 2 points, we choose those 2 points now and find their midpoint. The midpoint will definitely be a lattice point based on the way we structure this group. So the answer to this question is option E. That is 9. Yeah. It's just basically pigeon principle, but we have to like find a way to translate it from midpoint to physical quantities. Then later on, we'll try to use parity arguments before we're able to solve that. I remember the question wrote maximum, but I think it was a typographical error. It's meant to be minimum. So the minimum possible value of K is 9. So that's all we have for today, and I'll see you some other time.